Welcome. In this video, we're going to talk through some different types of spectroscopy. And so our goal here is to explain the relationship between a region of the electromagnetic spectrum and what's going on inside a sample of matter. And so spectroscopy in general is basically the interaction between light and matter. And by light, we mean different types of electromagnetic radiation. So the first step here is to understand that there are different types of electromagnetic radiation. There's various visuals that provide information about this. But if you're looking at your radiation going from highest energy to lowest energy, one of the lower energy forms of radiation is our radio waves. And then we've got microwaves, just like the microwaves that involve our microwave ovens in our kitchen. Then we've got infrared. Sometimes people use IR as a shorthand for infrared. Visible is kind of right there in the middle. And then we've got ultraviolet, right? So we use UV there. And then X-rays, like we maybe use the dentist or the doctors. And then gamma rays over there, our highest energy form of radiation. And these types of radiation differ by their wavelength and frequency. So the higher energy ones, they're over here. Notice how the high energy has a short wavelength. This is the symbol for wavelength. This is lambda, and they've got a high frequency. So if you look on your equation sheet, I'm going to use this notation because that's what they use on our equation sheet for wavelength and frequency. And we can see this visual, what that means. Short wavelength. Wavelength is the distance between these two peaks. High frequency, there's kind of like lots of peaks per second there. And then over here on the other side with your, and that gives it high energy. And on the other side, over here with like our radio waves, microwaves, notice how they have a longer wavelength and they've got a, smaller, I don't know what word we want to use there, lower frequency and a lower energy. So there's different types of radiation, different wavelengths, frequencies, gives them different energies. And then within the visible spectrum, and here, within that, you can break it down even further and look at the different colors of light. So notice how the red light over here has longer wavelengths, and that's lower energy. So the lower energy light is a red. And then over here, we've got the, higher frequency, shorter wavelength. That's your violet light. And that's the highest energy form of light there. And then using this radiation, here's another visual I like too, showing the different colors and the wavelength frequency. So again, the longer wavelength, lower frequency is lower energy, shorter wavelength, higher frequency, higher energy. And you don't need to memorize that relationship. Those relationships are given on your equation sheet. They look like this. So this tells you the energy and the frequency are directly related. And then there's this other equation, frequency times wavelength equals this constant, the speed of light. And that shows us that there's an inverse relationship. So the larger the wavelength, the smaller the frequency, or vice versa. So now let's look at these different types of radiation involved. So the first one we looked at was some emission spectra. And here is an example of an emission spectrum. I just realized it got covered up by my other visual. I'm going to move this up and away. Okay, so here's an example of an atomic emission spectra. What we see is we see these different types of these different bands of visible light that pop up. So this is what the data will look like. We'll see different bands of light of various wavelengths. And notice here how we're looking, within the visible spectrum. Sometimes we might also be, including a little bit of even UV or infrared there. And how the matter reacts is when you shine this, visible, ultraviolet visible radiation, that's associated with what they call transitions in electron energy levels. So let's call this electron transitions. And what we mean by electron transitions is that electrons are going to move between energy levels. All right, so that's what's going on when we have this UV visible radiation. It can cause electrons to move between energy levels. So we can either shine radiation at a sample that'll cause electrons to move, or we could add some other source of energy, and then when the electrons move, it's going to release visible radiation. And that's what we saw. We saw these bands of light be released there. Okay. Now let's look at another type of radiation. What if we were to, what happens with a microwave? And what happens is when you shine microwave radiation at a sample, it will cause something called transitions in rotational levels. So that causes molecular rotation. And we saw that in our PhET simulation when we shot microwaves at something, the whole molecule just kind of spun around, right? They were spinning around. So it's molecular rotation is what happens. That produces a type of data. This is what the graph might look like. We don't have to worry about interpreting microwave graphs, so don't worry about that. All right, infrared spectroscopy, that's another type that you can look at that involves infrared, or IR for short. And what happens is we shine infrared radiation at a sample. It causes what they call molecular vibrations, is what I'll call that there. And if you remember looking at this in the PhET simulation, what happened is it causes the bonds to kind of wiggle back and forth. So I'm just going to write that there. The bonds wiggle is what's going on there. And we say that the molecule is basically vibrating, like within the molecule itself. And that can also produce a data set that will tell us something about a molecule. This is something you might look at if you go into college organic chemistry. All right, then spectrophotometry, that also involves the UV visible range. So this also involves some electron transitions. And what we'll observe here is that we shine some light at a sample, some like UV or visible light, and it's going to, absorb the light, and that's going to cause the electrons to move. And what we'll find is different sample absorbs different wavelengths of light depending upon the structure of the atom. And I'm going to scroll this up here. A type of data set that we look at with spectrophotometry is we measure how much light is absorbed. And we'll find that different samples absorb different wavelengths of light based on the color of the sample. And we'll also notice that absorbance and concentration are directly related. So as a concentration increases, so does the absorbance. And we can actually write this out mathematically as something referred to as Beer's law, which is just a way of saying, hey, absorbance, which is A, is directly related to concentration. So this number goes up, this number also goes up. There is some constant here that relates these two variables, the concentration and absorbance. And if we're looking at this graphically, these two numbers would represent the slope of that line we're seeing on that graph. Because A is the Y, absorbance is the y-axis, concentration is the x-axis. So this right here is the relationship between the two, which is the slope of the line. So that's spectrophotometry. What happens, again, electrons are absorbing UV visible light. And then let's look at one other type of spectroscopy that we do want to know in detail, and that's photoelectron spectroscopy. And this is also sometimes known as X-ray photoelectron spectroscopy. So the type of radiation that we're shining on here is the X-rays. And we dug into some more detail with what's going on with the X-ray photoelectron spectroscopy, but here your electrons are absorbing the energy, and they're absorbing enough energy to actually leave the sample, and then those electrons that are being shot out are going to be measured, and we're going to get some data over here. And if we look at the type of data that we will see here, these X-ray photoelectron spectrographs, the key things we want to know about this one is that each peak represents a possible electron location, and we call those various locations subshells. So in this graph, we have 1, 2, 3, 4, 5 peaks. So if we see 5 peaks on the graph, that means that this atom has 5 subshells. And then the height of the peaks, so that is your y-axis. That tells us the number of electrons in that subshell. And then the location on the x-axis is the ionization energy And that has to do with how attracted the electrons are to the nucleus. So if the electrons are more attracted to the nucleus, then they are going to be harder to remove, which means they're going to have a larger ionization energy. So if we look at this graph, we notice this looks like this is argon. We've got 5 peaks. Notice this peak over here has the larger ionization energy. This one over here has the smallest. And we know that we talked about Coulomb's law tells us that the attractive force between two particles is proportional to the charge divided by the distance. So what that means is we know that distance and the attractive force are inversely related. So the closer they are, the smaller this number, the greater the attractive force. So these ones over here that are most attracted must be closest to the nucleus. So that means this peak corresponds to the 1s. This next peak must be the next furthest out. That's the 2s. And then this is the 2p. Notice how the height corresponds to how many electrons are in that spot. So we can hold 6 electrons in the 2p, but we can only fit 2 in the 2s. The next further out is the 3s. Looks like there's also 2 electrons there. And then we got the 3p. So photoelectron spectra is the graph we want to be the most comfortable interpreting, and then we've got separate practice sets going over those. But I also want to put it in the context of other types of spectroscopy. So again, we know that UV visible radiation causes electrons to move around. Microwave causes molecules to rotate. Infrared causes the molecules to vibrate, so the bonds are kind of wiggling back and forth. Spectrophotometry also involves UV visible, which electrons move around within the atom. And then X-ray is a higher form of radiation, and that absorbs so much energy, the electrons actually leave the atom, and that's what gets measured. There's another really important type of radiation, of spectroscopy, which is NMR, which gets used in research labs. And that's how that works is a little bit beyond the scope there. But if you look on our page in OneNote with this, if you're interested in digging into NMR, there's some references you can read or watch some videos about it. All right, hope this helps. Let me know what questions you have.